So now I'm going to tell you the high-level idea behind conjugate gradient descent, which does use the batch gradient. It's a very good technique, and this is the technique. It's the queen of techniques that uses the gradient. Okay, and I'm going to compare for you conjugate gradient with these three current winners. Okay, for motivation, and then I'll describe at a high level what's going on. And at a high level, what's going on is it's going to say, well, it's not necessarily optimal to move in the negative gradient direction, but we're going to use line search. So whatever direction we choose, we'll use a line search and in some sense make full use of the direction we have chosen. Okay, so here's a comparison on the right between conjugate gradient and steepest descent. And we know that steepest descent is comparable to stochastic gradient descent. And in the table, we're comparing the numbers. And you can see that, okay, if you optimize only for 10 seconds, then the methods are roughly comparable. Conjugate gradient is slightly better than stochastic gradient descent. But, once we move to, 1,000 seconds of optimization, the difference shows up. Conjugate gradient is much better. And then once we move to 50,000, there's no comparison. Conjugate gradient basically gets the error to zero. Okay. And all the other methods are lagging behind in running time, in optimization time. Okay. So you can read more about the details of conjugate gradient in the book, but here's the basic idea of conjugate gradient. So let me go back to this, contours of constant in sample error to illustrate the idea behind conjugate gradient. I'm going to draw this picture as big as I can without drawing my curves in weird ways. So here's the optimal W star. Okay. And let's say we're at some point W. Let's call this W of t. Okay. And so remember these contours of constant in sample error. So now let me draw them. Okay. Okay. And they're light, so you can't really see them that well, but they're there. I'm drawing them in red. Okay. Okay, so contours of constant in sample error. Okay. And so now you remember we choose the first direction. So let's say we're starting the whole conjugate gradient algorithm, and very often in the middle of the algorithm we reset it. So resetting means move in the negative gradient. So we move in the negative gradient. Okay, we move in the negative gradient. Okay, and as we are moving, maybe there's another contour in here. Okay, which is the one we get to for this line search for this iteration. Okay. Okay, so we move and move. Oh, so much for my abilities to draw curves well. Okay, so we're moving, and let's draw another contour here, which is tangent to that guy. Okay, another contour that's tangent to that guy. So where do we end up? We end up here. Okay. Now, what do we know? What do we know at the point where we've ended up after our line search is that the new gradient is orthogonal. Now that's nice, and I'll tell you what that actually means. That means that the gradient is when you take the dot product is orthogonal to the direction I moved in. Let me call this direction I moved in. Let me call this direction V. Okay, and this is the new gradient. So let me call this direction, this negative. This is G, the negative gradient. So this is G. My next gradient at the point where I stop. And what do I know? I know that G dotted into V is equal to 0. Okay, so let me tell you what that means. That means that I've set, so if you think of an orthogonal basis for my space in which V is one of the vectors, and you can always choose an orthogonal basis with, V as one of the vectors. If V is one of the vectors in my orthogonal basis, then I've set the component of the gradient in the direction of V to 0. Now, if I can succeed in setting the component of G in every basis vector's direction to 0. So if I can get, the components in any basis to 0 for, my D dimensional space, then I've got G equals to 0. And we're going for G equals to 0 because we're going for the minimum. And I've succeeded in getting one of the components to 0. Okay. So now the idea behind conjugate gradients is, well, if you move in this direction, as you move, you're going to change the gradient. Okay. And it's no longer going to be the case that the component in this direction V will be 0. Okay. So the question that conjugate gradients asks is there another direction to move? Okay. Is there another direction to move? Okay? So that as I move along this direction, okay, the gradient as I move along this direction, so I can compute the gradient as I move along this direction, and at all times the gradient should stay parallel to the previous gradient. So I don't want the gradient to change in, its direction. Okay, and then when I stop, okay, so here's my new gradient. I know that since it stayed parallel to the previous gradient here where I started, that means that my new gradient is orthogonal to V. And since this is the place where I stopped, okay, my new gradient is orthogonal to this new direction V prime. Okay? And as long as V and V prime are linearly independent, I have succeeded in setting the component of the gradient in two independent directions to 0. Okay? And then I use that same philosophy for the next step. So I have a gradient. Okay. Can I move in a new direction that keeps the gradient parallel to what it was before, but then when I stop, it's now perpendicular to my current direction, and it still remains perpendicular to the previous two, because it's basically parallel to the previous two. Okay, so that's the philosophy behind conjugate gradients, to choose each next direction so that as you move along that direction, okay, the gradient doesn't change. Or more specifically, the dot product of the gradient with respect to the previous direction that you moved in doesn't change. Okay. Now, we can do all the math and figure out what that direction is. And it's a very well-defined direction if the surface is actually quadratic, which means if the surface, which will be the case as you get closer and closer to the optimal. And that's what you see in that picture, that as the error gets lower and lower, the other methods start faltering, but conjugate gradient gets to the minimum very efficiently. Okay. And in fact, it's possible to prove that, if you're in a quadratic error surface, then, it's possible to exactly accomplish all of these. And in exactly these steps, you will have gotten the gradient orthogonal to D linearly independent directions. And so you can prove that conjugate gradient will stop in D steps. Wow! What a beautiful algorithm. In practice, we run conjugate gradient for D steps or maybe D over 2 steps and then restart. And that's because the error surface is not completely quadratic. Okay. And there you see the performance. The proof is in the pudding. Okay, the proof is in the pudding. It kills stochastic gradient descent. Now, one of the challenges with conjugate gradient is, you need to compute the gradient and you need to do a line search. And if your data is distributed and so on and so forth, then it's not easy to do these operations. And that's one of the reasons why stochastic gradient descent is so popular, because data is distributed. And when you're running the algorithm, you just need to go to the server that stores the particular data point you want, compute the gradient, make the move. Okay, it's very efficient. Okay. Now, all the methods that we have discussed only use gradient information. If you're allowed to use Hessian information, then you can do even better. Okay. In fact, the conjugate gradient algorithm for a quadratic surface gets to the optimal in D steps. The second order methods for a quadratic surface gets to the optimal in 1 step. Okay, so that's the level of improvement from D to 1. Okay, but then you can combine, Hessian information, second order information with line search and do better and better. Okay, so just to show you some of the spectrum of the algorithms that you can implement when you're trying to optimize a neural network. And that's a big deal these days because the neural networks are large and the data sets are huge. Okay? And my recommendation, until you get to the point where data has to absolutely be distributed across, multiple servers, you cannot beat conjugate gradient. That's the queen of the methods. And there's the proof in the pudding. Okay, we're looking at optimization time. It kills the heck out of stochastic gradient descent. But stochastic gradient descent is a pretty decent algorithm. It's very flexible with respect to parallelization, distributed data, and so on and so forth. So some of the things that people are thinking about these days, from the more algorithmic side, from the point of view of the second step of machine learning, which is to get the in-sample error low. And we are computer scientists. We have to think both about the algorithmic side and the statistical side. The first step, E in versus E out. E in has to be close to E out. Otherwise, there's no point going for low E in. Okay, so that concludes our discussion of neural networks. You've basically seen the entire package, which is why we need neural networks. They are awesome power. Okay, how to fit them and then how to control them. Okay, and one of the, you can read a little bit about in the text about some of the motivation behind deep networks. How when you use deep networks, okay, each layer sort of has a representation of a feature of the data or of the problem at a different level. So low level features, then higher level features, and so on up to the final highest level feature. Okay, so you can read a little bit about it in the text, in the e-chapter. Okay, and of course, there are books and books being written about deep learning. Well, I don't have a specific recommendation there, but one recommendation I will give you is stick to the foundations, stick to the fundamentals, and you've seen the whole package. Okay, checking out.